Hello, everyone. Welcome. Good afternoon. Hope you're doing well. Glad to see some of you are getting vaccinated. They just opened it up to everyone 16 and over, it looks like, in Santa Barbara County. And so I put a link in the chat. If you have not been vaccinated, click on that link and try to make an appointment. I'm not sure what the availability is at the moment, but they keep adding more. So you just got to keep checking back. And sometimes you just got to sit there and search over and over again, and maybe one will come up from someone canceling. So definitely worth it. And the sooner we all get vaccinated, the sooner we all get back to normal. So just go up in the chat. It's still in there. If you just go up in the chat, you should be able to see it. I can resend it though. Yeah, we'll resend it right now. There you go. Yeah, so super exciting, right? And the vaccines are really working. You look at places like Israel and the UK, where they have a significant fraction of their population vaccinated, and it's going really well there. And we're getting there in the US as well. So do your part and go out there and get that vaccine, okay? If you haven't already. Congratulations to those of you that already got it. Okay, we are in chapter 20 on electrochemistry, and we're ready to jump in here. Before I get started, do you have any questions for me? Yes, it's part of your homework to go get your vaccine. The first shot is not as bad. The second one has some side effects. My wife and I both felt kind of yucky for a day, but we took Tylenol and we got through it, and it wasn't that big a deal. So, yeah, extra credit. Let's see. Any other questions? All right, I don't hear any. Oh, Megan, I feel you. Take some Tylenol, and if you feel really cruddy, just let me know, and I can try to. If I do make some exceptions on due dates and things for family emergencies and health reasons. So if you have a health emergency or a family emergency, right, you should always contact me, because I'll work with you on that. Okay, and certainly feeling crappy from the vaccine is sort of a health emergency. So don't cancel your appointment. Okay, Megan. All right, let's jump into balancing redox equations, because in order to deal with electrochemistry, we've got to be able to balance these redox equations. So last semester, we learned how to balance just normal everyday equations. Redox reactions require a special kind of procedure to balance them. Okay, so let's go ahead and jump into that. The first thing we got to do is review a idea from last semester called oxidation state. Do you guys remember oxidation states? So an oxidation state is a charge an atom would have in a compound if all bonding electrons are assigned to the more electronegative atom. All right. That's different than formal charge. Okay. Formal charge is a charge it would have if all the bonding electrons were split equally. So we have different ways of accounting for electrons. And here we want to focus on oxidation state. So I'm not going to review the rules right now because we've already done them. If you can't remember them, review section 5.9 in your book, right? And that's the rules for assigning oxidation states. You'll need to know that, okay? So these are them. I'm just going to flash them up here for a second, but like I said, I'm not going to go through them because we don't have enough time really. And we already covered these. So again, just review that section in your book. It should come right back to you, okay? When you have a redox reaction like this, all right, you can assign oxidation states, and from that you can tell what's being oxidized and what's being reduced, right? So if you have, let's say, calcium solid plus 2 H2O goes to CaOH2 aqueous plus H2 gas. right? You can take an equation like that and assign oxidation states, all right? Calcium, this is all, you want to take a quick screenshot of that? This is all in your book in section 5.9, all right? And it's presented really nicely there. So if you can't remember it, just go back and do that and then look there, okay? But calcium is a pure element, so that gets an oxidation state of 0, right? Normally for a lot of compounds, you start with oxygen. Oxygen is -2, and then you can figure out from that each hydrogen is +1, all right? Here, again, if we start with oxygen -2, hydrogen +1, and we see that we have 2 OH minuses, right? So calcium must be +2, okay? And then this side, we got a pure element, so that's 0, all right? So remember again from last semester too, the definitions of oxidation and reduction in terms of oxidation state, right? Does anybody remember that? What is how can you tell from oxidation state if something's being oxidized?
Isn't oxidized losing electrons?
Correct. It's losing electrons. You're right. And what about the oxidation state of something that's being oxidized? What happens to its oxidation state?
It increases in the oxidation state.
Correct. Correct. So we can see here, right? The calcium is going from 0 to +2. So that is being oxidized. Okay, so that's our oxidation, all right? What's being reduced here? And a reduction is a reduction in oxidation state or a gain of electrons.
Is it hydrogen?
Yep, hydrogen's being reduced. So hydrogen is going from +1, right, to 0. And that is a reduction. Okay, so in order to balance redox reactions, you got to be able to do this. That's the first thing you do. You assign oxidation states to everything. You determine what's being oxidized and what's being reduced. Okay. So let's look at another example here. This is the combustion of methane. If we assign oxidation states, we see that carbon goes from -4 to +4. So that's being oxidized, right? And here oxygen's going from 0 to -2, that's being reduced, okay? So when we balance redox reactions, here is the procedure we're gonna follow, okay? We're gonna, and instead of reading through all this, I'm just gonna do a couple of examples and work through it, and we'll work through it together, okay? So the first example I wanna do is this one. So let's write that down. The reaction we want to balance is Cr2O7 And I'm going to leave out the aqueous because everything's aqueous except for the I2 plus I minus goes to Cr3 plus I2. All right, so that's the equation we want to balance. And now we're just going to go through these steps to try to balance it. Okay. So first, we're going to assign oxidation numbers, okay? So work through this with me. What would oxygen be right here?
-2
Negative
times
2.
7.
-2, right? So each oxygen is -2. There's 7 of them. So together they're -14. The entire ion is already -2. So that means that the 2 chromiums must each be how much? Can anybody figure that
7.
out?
Oh, wait, no.
Not
6 at top.
6.
6. Yes, +6. Exactly right. So each chromium is +6. Okay. Here we have I minus. It's a monoatomic ion, so it's just -1. Here's chromium 3 plus, monoatomic ion, so that just equals its charge. 3 plus. Sorry, +3. And then I2 is a pure element. So what's its oxidation state?
0.
0. Okay. So who can tell me what's being oxidized here?
Iodine.
Correct. Iodine's being oxidized. It's going from -1 to 0. So that's the oxidation, right? what's being reduced?
Chromium.
What is it?
Chromium.
Chromium's being reduced. It's going from +6 to +3. So that's the reduction. Okay. So that's the first step. Assign oxidation data, determine element oxidized and element reduced. We've done that. Okay. Step number 2, we're going to write half reactions for the oxidation and the reduction. All right. That means we're going to separate out one from the other. Okay. So we'll start with the oxidation. The oxidation we said is I minus going to I2. So we're going to write I minus going to I2. That's the oxidation half reaction. Okay. And then we'll do the reduction half reaction. Reduction half reaction is Cr2O72 minus. And that's going to Cr3 plus. All right. So notice we've assigned oxidation numbers. We figured out the oxidation and reduction half reactions. And now we're going to start the process of balancing. Okay. But again, it's not just willy-nilly balancing. Okay. You have to go in a certain order, and you have to be really strict about this. If you mess this up, if you go in a different order, you basically have to start over. Okay. So just be really methodical when you follow these rules and you're balancing these reactions. And if you do that, you'll get it right every time. Okay. So the first thing you're going to do is you're going to balance elements other than hydrogen and oxygen. All right. So in this first half reaction, we have 2 iodines and only 1. So we're going to put a 2 here, and that's balance. Right. In the second reaction, we have chromium, 2 of them here, only 1 of them there. So we're going to put a 2 on this side. And now the chromium's balanced. Okay. The only other elements left in all of this is oxygen, right? But remember, first we're on step 3A here, first balance elements other than hydrogen and oxygen. Okay. Now the part B of step 3 is to add water to balance oxygen. Okay. Well, we have 7 oxygens over here, right? So to balance out, we're going to need 7 waters over here. All right. And now oxygen is balanced. Go on this part C, add H plus to balance hydrogen. All right. How many hydrogens on this side?
14.
14. So we're going to need 14 H plus over here to balance those 14 hydrogens. All right. This D step here, 3 part D, only applies to basic solution. Okay. So this particular one that we're doing here is an acidic solution. Forgot to write that at the beginning, but this is an acidic solution. So that means we don't have to do that step. After this example, I'll do one in basic solution so you see what that looks like. Okay. Next thing is you balance the half reactions according to charge. All right. What that means is that the charge on both sides of the half reactions have to be the same. All right. And the way you're going to balance the charge is only by adjusting the number of electrons, by adding electrons to balance the charge. All right. So notice this reaction has a charge of 2 minus on the left. So if I'm going to add electrons to balance the charge, what am I going to do? I'm going to add 2 electrons to the right. Right? Because that gives me 2 minus on both sides. Does that make sense?
Yes.
On this one, I have 2 times 3 is 6 plus on the right. And I have 2 minus on the left, right? So 6 plus, let's see, is that right? 2 Cr2 plus. So let's go. Oh, sorry, forgot the 14H plus. You have 3 plus, you have 6 plus on the right, and you have 12 plus on the left, right? Because I have 14 plus minus 2 is 12 plus, so I have 6 plus, 12 plus and 6 plus. 12 plus, and 6 plus, right? So in order to balance that by adding electrons, right? How many electrons am I going to add to which side?
6 to the right.
Okay, if I add 6 electrons to the right, that's going to make the
To the
right
left.
side 0, and this side still is 12 plus. That's not balanced, right? You don't want to make the charges 0. You want to make them the same. That's a common mistake, though, so be careful. You don't want to make the charges 0. You want to make them the same. So in other words, I want to get this side to be 6 plus, right? Because I'm only going to add electrons, so I can only make the charge more negative, right? So how many electrons to which side?
6 to the left.
6 to the left, correct. So 6 electrons plus that. Now that brings this charge down to 6 plus, right? 14 plus minus 2 is 12 plus, minus 6 is 6 plus. Are you with me? All right. So I balance the charge. Now, the next thing is to balance the electrons between the half reactions. And what I mean by that is that the number of electrons, actually one more thing before I forget. At this point, you should always be adding electrons. You should go back and check. Okay, oxidation is what? The loss of electrons, right? That means that the electron should be on the right-hand side. In fact, that's the case, right? Reduction is the gain of electrons. So electrons should be on which side?
The left.
The left, right? And in fact, that's the case. Okay. So the next thing to do, number 5 there on the list, is to make the number of electrons gained and lost equal, right? Because you can't have 2 electrons lost here and 6 gained here, right? Where did they come from, right? So you got to make them equal, all right? Let's see, the oxidation reaction. The oxidation reaction is going to, okay, since oxidation is, sorry, I had a question about the oxidation reaction. The oxidation reaction is, since you know oxidation is the loss of electrons, right? Electrons should be on the right. Okay. All right. Now we got to make the number of electrons equal. We have 6 here, 2 here. How can we make them equal? We can multiply this one by 3. Right? We can multiply that reaction by 3. Then we're going to have 6. So again, here's my oxidation. 6I minus going to 3I2 plus 6 electrons, right? Okay, and if I bring my reduction down, my reduction is 6 electrons plus Cr2O7 2 minus plus 14H plus goes to 2 Cr3 plus 7 H2O. All right, so there's my oxidation reduction half reactions. I've balanced the mass, I've balanced the charge, and I've made the electrons equal. I only have one step left other than checking, and that's to add the half reactions together. When you add the half reactions together, since you've made the number of electrons equal, the electrons should always cancel out exactly, right? 6 lost here, 6 gained there, okay? So when you add these reactions together, I'm going to end up with 6I minus, oops, I forgot my minus here, didn't I? 6I minus, that's from there, and then plus Cr2O7 2 minus plus 14H plus, right? They're all my reactants. What are my products? 3I2 plus 2Cr3 plus 7 H2O. Okay, and that should be the balanced reaction. Now, you never want to stop there. You always want to check to make sure you did it correctly, right? So let's just go through and check. How many I minuses are on the left side of this equation?
6.
6, right? And how many I's are on the right side of this equation?
6.
6.
6, right? So I checks out, okay? Chromiums, I have 2 on this side. How many on this side?
2.
2. So that checks out. Oxygen, I have 7 on this side, 7 on that side, right? So oxygen checks out. Hydrogen, 14 on this side. How many on the right side?
14.
14, right? So everything is balanced. The only other thing you got to check is the charge balance, okay? You can't have charge appearing out of nowhere. The equation also has to be balanced with respect to charge, all right? So the left side, the total charge is -6, -2 is -8, right? Plus 14, the total charge is +6, right? 14 minus 2 is 12, -6 is +6. On this side, the total charge is 2 times 3 plus 6. All right. So the great thing about these redox reactions is you can always check yourself to make sure that you balance it correctly simply by checking the mass first and then the charge. Does that make sense? Any questions?
I'm sorry. Just before like starting the balancing, how would I realize it's a redox reaction? Just because there's charges on.
The only way to know for sure is to assign oxidation states and see if there's any change in oxidation states.
Okay.
Okay. When you see a change in an oxidation state, then you know it's a redox reaction. There are many reactions in which oxidation states do not change, and those are not redox reactions, obviously. Okay. But that's what you're looking for. Now, a lot of times you can tell pretty quickly, right? Because, for example, here you have I- and you have I2, right? And you know the pure elements are 0 and this has a charge of -1. So you know this has to be a redox reaction, right? Up here, same kind of thing. You have pure calcium on this side and you have a calcium 2 plus ion here. So you know that's a redox reaction. Okay. Now, for balancing, you know, I'm going to always say, balance this redox reaction occurring in either acidic solution, in which case you follow this procedure like we just did, or in basic solution. So let's do an example in basic solution. All right, our example for basic solution is this one. MnO4 minus plus Br minus goes to MnO2 plus Br2, okay? And we're just gonna follow this same procedure one more time, except the only difference is this step D right here, okay? We're gonna add in this extra step. All right, so oxidation states first. Oxygen -2, there's 4 of them, that's -8. So what's the oxidation state for manganese?
+7.
+7, correct. Br minus, just -1. On this side, oxygen is -2. There's 2 of them. So what's manganese on this side?
2. Oh, sorry, 4.
+4, correct. And then bromine's a pure element, so it's 0. Okay. So let's see, what's being oxidized?
Bromine.
Bromine, right? Bromine's being oxidized. And what's being reduced?
Manganese.
Manganese, correct. Manganese is going from +7 to +4. Okay, so now we've done this step 1. We're going to go to step 2, write the oxidation and reduction half reactions, right? So oxidation first. Oxidation is Br minus going to Br2, right? And the reduction is MnO4 minus going to MnO2. So far, so good? All right, then we're going to balance the mass, and then first elements other than hydrogen and oxygen. So we got 2 here, we got 1 there, so we're going to put a 2 here. Manganese, manganese, there's only one on each side, so manganese is already balanced. Okay. Next step, add water when you need oxygen. So we got no oxygen here, so we're fine. In the reduction reaction, we got 4 oxygens on the left, 2 on the right. So how do we balance that?
Yeah, 2 waters
Add 2 waters to which side?
to the left.
To the left?
Oh, the right, sorry. I was like,
Right, to the
the
right.
right. I mean, I'm an O2.
So there's our oxygen. Next thing, add H plus. So what do we got? We got 4 H's here, so we are going to add 4 H plus to the left, right? And then here comes the unique step for basic reactions, right? Neutralize with OH minus, okay? So what I'm going to do is I'm going to say, okay, I have 4H plus here. I'm going to neutralize with that with OH minus, but I don't want to mess up the mass balance, right? So when I add OH minus, I got to add it to both sides, right? So I'm going to add plus 4 OH minus to this side, but I'm also going to add it to that side, okay? To both sides. So this becomes, my reduction then becomes MnO4 minus plus. Now what's 4H plus 4OH minus?
4 waters.
4 waters, right? That becomes 4 waters, right? And that's going to go to MnO2 plus 2 H2O plus 4 OH minus. Okay, so now this is my oxidation, and this is my reduction.
Are we supposed to add electrons too?
Yeah, we're only here on step 3D. Okay, so remember, you always want to do this in exactly this order. All right, if you don't follow the order, you'll get thrown off track and you'll have to start over. Okay. All right, now step number 4 is we balance the half reactions with respect to charge, and this is where we add the electrons, right? So let's look at the oxidation half reaction. 2 minus on this side. If I'm going to balance it with electrons, what do I add?
Plus 2e to the right side.
Right. 2 electrons to the right side. Okay. Now that's balanced with respect to charge. Here, now always make sure, right? That's an oxidation. On which side of the equation do electrons belong in an oxidation half reaction?
To the right.
On the right side. That's correct. All right. Let's see. Quick question, Megan.
I was just wondering, for when we were doing the reduction with the waters and you combined the 4 waters on the left side, why don't you do something similar to the right? Can you not do like combine the hydroxyl group?
Great question. The reason this becomes 4 waters is because remember, this is 4H plus 4OH minus, right? So that's an acid. H plus OH minus makes water right away, right? That's like an acid-base neutralization, right? So they neutralize each other and make water. H2O plus 4H plus, there's no reaction there, right? There's no reaction between those. So the 4OH minuses just stay as 4OH minuses. There's no H pluses here to neutralize them. Does that make sense? Great question. Okay, so down here then for the reduction, right, we have a charge of 4 minus on the left, 4 minus on the right, 1 minus on the left. What do I need?
3 electrons on the left.
Correct. Plus 3 electrons, right? Everybody with me to here? Questions? Okay, very good. Now I can add together the, oh no, sorry, I can't add them together yet. I still have to do one more thing. What do I have to do? make the number of electrons
Balance the
equal.
electrons.
Right, I have to make them equal. So in this case, I have 2 electrons. In this case, I have 3. So how am I going to make them equal?
Multiply 1 by 3 and the other by 2.
Correct. I'm going to multiply this one by 3, and I'm going to multiply this one by 2. Okay? And that's the only way I have to make them equal. So writing down here then, my oxidation half reaction becomes 6 Br minus, right, goes to 6 electrons plus 3 Br2. Right? My reduction half reaction becomes 2 MnO4 minus plus 8 H2O plus 6 electrons goes to 2 MnO2 plus 4 H2O plus 8 OH minus. Does that make sense? Awesome. The next thing is to add the half reactions together, right? So now I'm going to add these together. And again, every time you add them together, what should happen? The electrons should cancel out. So I got 6 electrons there as products, 6 here as reactants, so they cancel, right? Now, notice that I have some other things that I can cancel out here as well, right? I have 8 waters on this side and I have 4 waters on that side, right? So that's an extra 4 waters. So I can say 4, and this goes from 8 to 4. Okay. Then I can add everything together. I'm going to get 6 Br minus plus 2 MnO4 minus plus 4 H2O goes to, so I've got all the reactants here, right? 3 Br2 plus 2 MnO2 plus 8 OH minus. Okay, let's check it, right? How many bromines on the left?
6.
6. How many on the right?
6.
6.
So that's good. How many manganese on the left?
2.
2. How many manganese on the right?
2.
2. That's good. Oxygens on the left. I have 2 times 4 is 8, right? Plus 4 is 12. So I have 12 oxygens on the left. How many on the right?
12.
4 plus 8, which is 12?
It's 8 plus 2 times 2 is 4 is 12 as well,
Yes.
right? So I have 12 on both sides. So that's good. And then lastly, hydrogen. How many on the left?
8,
8. How many on the right?
8.
8. Okay, so all of the elements are perfectly balanced. Next thing is the charge. What's the total charge on the left?
8?
Yep, 8 what?
Negative 8 electron.
8
Wait,
minus, right? 8 minus on the left. What's the total charge on the right?
8
8
8
minus.
minus.
8 minus. Yay! Right? So the whole thing is balanced. Okay? So it's a little bit of a procedure. The key to this is to take it slow and be very methodical, right? Follow this to the T and you'll get every one of these right every time. Okay? Veer away from this and you'll make a mistake. Abe.
Yeah, I'm still a little confused on how you automatically knew to multiply by 3 and 2.
Oh, okay. Yeah, because here I have 2 electrons and here I have 3. So somehow I got to get them
Oh,
to
okay,
be
okay,
equal,
okay.
right? And so I can't, sometimes you can just multiply one equation to get them equal, but in this case you can't, right?
Mhm.
So you're looking for sort of the lowest common factor, right? The lowest common factor is to say, oh, okay, if I multiply this by 3, then I get 6 electrons. If I multiply this by 2, I get 6 electrons.
I get it. Thank you.
Yeah, good question. Sophia.
Sorry, just confused on how you got the charges. You just multiply the 2 by the 4 times the -2.
Okay, so the charges
Oh,
are remember,
negative
this is 2 MnO4 minus ions, right? So each ion is -1. There's 2 ions, that's 2 minus. And then I got 6 Br minuses, so that's 6, and 2 is 8
Oh, okay.
minus.
Okay, thank
On the
you.
right-hand side, I just have 8 OH minuses, so that's 8 minus. Does that make sense?
Yeah, thank you.
Okay, you're welcome. So there was a question about whether we can cancel out the water right after the H plus and OH minus neutralization. Yes, you can do that. You can do it there or you can do it here, either way. And counting the charge. Counting the charge, you just add up the positive charges and the minus charges, right? So I have 6 minus and 2 minus is 8 minus, and here I just have 8 minus, right? So what you want is for the charges to be equal in the end. Okay. All right, any other questions? All right, very good. All right, I'm not going to do a poll on this because you're going to have some practice on your problem set, and I want to move on and get to some other things. But you'll get more practice on this on your problem set. I guarantee it. And you'll, of course, see something like this on the next exam. So make sure you know how to balance redox reactions. Oh, there was one more question, Sophia.
Just curious, why do we neutralize with OH for basic reactions, but not for acidic reactions?
Oh, great question. Because in acidic reactions, right, at the end, you're going to have H plus present, right? But if it's in a basic solution, H plus can't really exist, right? Because the bases will cancel it, will neutralize it. So that's why we have the OH minuses to neutralize it as it would happen actually in the solution that's basic.
Okay. Thank you.
Yeah. Okay, great. All right, let's move on to electrochemical cells. So remember last time I said, look, here is a spontaneous redox reaction, right? You have zinc and copper 2 plus. So you have copper 2 plus in solution. You have a solution of copper 2 plus. You have a zinc metal you put into it, and you get a spontaneous oxidation reduction reaction, right? The electrons go from the zinc to the copper 2 plus, right? The zinc oxidizes, it becomes zinc 2 plus. The copper 2 plus reduces and it becomes copper solid. And that's the brown stuff you see growing here, right? That's the copper 2 plus depositing as copper solid, right? You see the blue color fade as the copper ions are taken out of solution. If you could see zinc ions, you'd see the zinc ions forming in this solution, okay, as a function of time. So this is before and after the reaction, okay? Now, the key to understanding an electrochemical cell, remember, electrochemical cell is a way that you can take a reaction like this and force it to create electrical current, okay? You can force it to create electrical current. So you separate out the two half reactions so that the electrons can't go directly from the zinc to the copper, but rather have to go through an external circuit, right? Because this reaction has this tendency to happen, right? The copper 2 plus draws the electrons more strongly than the zinc can hold them, right? So it has a tendency to happen, and it'll happen even if the two are not in contact with each other, right? As long as there's an electrical pathway for the electrons to go, all right? And that's how we build what's called an electrochemical cell. And in this case, we call this particular type of electrochemical cell a voltaic cell. A voltaic cell, right, is one that occurs spontaneously, right? And it produces positive voltage, okay? And we're going to learn more about that in just a couple minutes. But let's just take a look at this electrochemical cell. So here you have zinc, metal, and zinc 2+ solution. On this side, you have copper metal and copper 2+ solution. All right? The electrons have higher potential energy at the zinc, and that's why they travel over to the copper where the potential energy is lower. All right? And if you watch the video, right, you learn a little bit about the difference in potential energies between these half cells, okay? So that happens spontaneously and it would light the bulb, and this is a voltaic cell. The electrode where oxidation occurs is called the anode. All right? And the electrode where reduction occurs is called the cathode. Luckily, anode and oxidation both start with vowels. Cathode and reduction both start with consonants, so you can remember it that way, okay? Oxidation always occurs at the anode, all right? So electrons start to flow, they light this bulb. The reason they flow is because they have higher potential energy here than they do here, so they go downhill, right, towards the cathode. If that was it, what would happen is that the electrons would flow out of here and you'd build up negative charge over here, right? And because there's no way for the charge to equalize. In other words, there's no way for the circuit to be completed. The electrochemical cell would immediately stop. It would stop functioning, right? Because of charge buildup. So you got to put in something that completes the circuit. In most cases, you can use something like this called a salt bridge. A salt bridge just contains usually some glass wool, all right? Which looks like, you know, kind of like fiberglass wool, if you've ever seen that sort of thing. And it contains, in this case, some ionic compound like potassium nitrate, all right? And what happens is as the negative charge builds up on this side, that draws in the potassium ions to neutralize it, right? And as the negative charge goes away from here and positive charge builds up over here, the negative ions come over to neutralize that. And that completes the circuit and makes this cell a full electrochemical cell that can continue to operate. Okay?
Why does they need to be neutralized for it to operate?
So remember all along, you know, we've sort of talked about, can you have just like, let's say you had a solution of just positive charges, right? Remember, that sort of thing doesn't really exist, right? Because whenever you have charge buildup, the charge is going to neutralize, right? You see that in the thundercloud, right? As soon as you have charge separation, you get big results, right? You get big bolts of lightning, right? Because charge wants to neutralize each other. So most of our world is pretty charge neutral, right? When charge builds up, it equalizes, okay? You notice that, you know, when you get static electricity, for example, when you walk across a carpet on a dry day, right? You get a few extra electrons in your body, right? But it doesn't last that way for long. The minute you touch something metal, that's going to neutralize. So it's the same idea. You can't just have a buildup. In other words, electrons can't flow in one direction forever without neutralizing that charge. Taylor?
Yeah, my question was on the salt bridge part. So the negative charged ion goes to the negative. How did I say this?
Yeah, the negatively charged ions go to the anode side.
Okay.
The anode is negatively charged because notice the direction of electron flow. Electrons flow from negative to positive.
Mm-hmm.
Okay, so the anode is negatively charged. The cathode is positively charged. That's the way we label them.
But the liquid is positive in that, or no?
Well, the liquid contains, so the liquid here contains is going to be forming zinc 2 plus. But remember, the solution is zinc nitrate, which is charge neutral, right? These solutions have to pretty much stay charge neutral. As the negative charge leaves this side, it begins to build a positive charge. So more nitrate ions come over to neutralize that.
Okay. So that's what pulls them over. is
Correct.
that-
Correct.
Okay.
Yep.
Thank you.
So if there wasn't a salt bridge there, would the electron flow stop or would it keep going?
Yes, that's exactly what would happen. It would go for an instant and then it would just stop. Correct.
So it's basically like the flow of electrons is what's powering it.
Correct. Yep. And the reasons electrons will continue to flow as long as you can deal with the charge neutralization is because the electrons have higher potential energy here than they do here. But as soon as this acquires a bunch of negative charge, then that potential energy difference would no longer exist, right? So that's why you need the salt bridge. Okay, good. Now, I want you to understand a couple of simple things about electrical current. A good way to think about electrical current is like water flowing down a stream, okay? If you think about a stream with water flowing through it, that's kind of like electrons flowing through a wire, okay? Two important pieces of information. The first one is the current. What's current in a stream? It's the amount of water that's flowing per unit time, right? The more water that flows through per unit time, the higher or the stronger the current, right? If it's just a little trickle of water, then that's a very small current, yeah? Same thing for electrons. If you have a lot of electrons flowing per unit time, that's a very high current, right? If you have just a trickle of electrons flowing, that's a very low current. We measure current in a unit called amps. And 1 amp is equal to 1 coulomb per second. And I don't know if you remember the unit coulomb from last semester, but coulomb is a unit of charge, right? 1 electron has a charge of negative 1.6 times 10 to the minus 18 coulombs, all right? So that's how we measure current, is just charge per unit time. Okay? Now, what about voltage? If the current of the flow of electricity is like the current in a river, right? Then the voltage is analogous to the steepness of the river, right? Because the voltage represents potential energy difference. In fact, it's called potential difference, but it's really potential energy difference, okay? It's the difference in potential energy between this side of the wire and that side of the wire. Well, what's the analogous thing in a river? The difference in potential energy of the water from one part in the river to another part of the river. And that depends on what? The steepness of the river, right? So in other words, a electrical circuit that has high voltage is like a river that's really steep, right? The steepness of the river is the driving force, right, that makes the water go. It's the difference in potential energy between one part of the river and another, right? That steepness is what drives the water to flow down the river, right? Similarly, the difference in potential energy, the voltage, is what drives electrons to flow through a wire, okay? So you can have, just like in a river, you can have high current, but not very much steepness, right? Think of some of these rivers that go along, you know, the middle of the country where it's pretty flat, but they still flow. They don't have a lot of voltage, but they have a lot of current, right? But you need some voltage to keep the river flowing, right? You need, otherwise it becomes a lake, right? So you need some steepness to keep the river flowing. So you can have a lot of current, not a lot of voltage. You can have a high voltage, but not much current, right? Anybody ever hike up to Tangerine Falls in the fall, right? Tangerine Falls up here off of Cold Spring Trail. If you hike up there in the spring, you'll see a nice waterfall, a lot of voltage and some current. But if you have up there in the summer, you'll see a cliff, right? High voltage, but no current. Okay? Does that make sense to everyone, the difference between voltage and current?
Wait, Troy, did you say current is analogous to the speed of the river?
Correct. The amount of water flowing through the river is actually is closer to what the mean of current is. The amount of water flowing through the river per unit time.
Would
And-
that make voltage sort of like acceleration then?
One more time.
If current is like the velocity, would that make voltage sort of like an acceleration?
So it's a little different than that. So current is not really velocity. Current is the amount per unit time, right? So
Okay.
it's the amount of water flowing per unit time in a river. It's the amount of charge flowing per unit time in a wire. Voltage,
Okay.
voltage is analogous to the steepness of the river, right? How steep it is, because voltage is the driving force that drives electrons down the wire, just like steepness, a change in elevation, is the driving force that drives water down a river, right? So that's the analogy. Taylor?
So is that why like bigger wires can hold more voltage? 'Cause they
Correct.
have, like,
Yep,
More-
they have less resistance. So
Ah.
resistance would be like having big boulders in the river.
okay.
It slows the water down, right? That's resistance. The more if you have a really smooth bottom river, like, some of the canals that they've built out in Carpinteria that are cement lined, right? That would be low resistance, right? If you have rivers like you have in
Mhm.
Montecito that got all clogged up during the big storm, a couple years ago from the fire, right? That would be high resistance, right? And water doesn't flow as well, right? As we all found out. Okay?
Because I've only heard the analogy being like the width is voltage, never like the slope. So I
No,
don't
the slope is the
think I'm
voltage.
wrong.
The slope,
slope
is
is the
analogous to
voltage.
voltage. Correct. The steepness of
It's
the
not
river,
like a
not left to right. No,
okay, not like a width deal.
up and down.
Okay.
Yeah. The difference between here and here.
Okay.
Okay, so now, some electrochemical cells like this, right? Some of them have higher voltages than others, okay? Some of them have a more strong driving force than others do, okay? So for example, if you have this electrochemical cell where you have zinc and copper 2+, and we measure the voltage of that cell, and we can do that by putting a voltmeter here, we would find the voltage is 1.10 volts, all right? But if you had nickel instead of zinc, the tendency for this reaction to happen is not as strong as the tendency for this reaction to happen, so the voltage is lower, okay? So the voltage that you measure is a measure of the steepness of the slope, right? From here to here, right? How much difference in potential energy is there from here to here? A high voltage means a big difference in potential energy. That's like a river that's very steep. A low voltage means that there's not that much difference in potential energy. So that's like a river that's more flat. Yes. I saw this question about neurons and muscle cells. That's exactly what they are. They are little voltaic cells. And because of changes in ion concentrations, they have a voltage, and that voltage can change. And that's the way nerve signals travel throughout our body and in our brain. Yep, absolutely right. Correct. Okay. All right. Standard electrode potentials. So, remember when we looked at free energies and entropies and all that stuff, we created these tables that allowed us to calculate changes in free energies and changes in enthalpies for chemical reactions, all right? Standard electrode potentials are a way that allow us to calculate, to build a table that allows us to determine voltages for electrochemical cells, okay? So it's kind of analogous to what we've done before, all right? And you know that whenever we do that sort of thing, we have to establish a zero, right? We have to establish a zero. What do we call zero? All right. So we're going to do the same thing when we assign these standard electrode potentials. Again, with analogy to water, and if you watch the video, you saw this, right? Some half cells, like let's say this one, zinc in a zinc nitrate solution, is analogous to a beaker that has a lot of water in it, right? The water at this top of this beaker, right, it has high potential energy. Just like electrons in this half cell have high potential energy. Why do they have high potential energy? It's just the nature of zinc, right? For the electrons to have high potential energy when they're in zinc metal, all right? Electrons over here in copper metal have lower potential energy, okay? And so the electrons are going to flow from high potential energy to low potential energy, just like water flows from a beaker where it has high potential energy to a beaker where it has low potential energy. It's exactly the same thing, all right? Here we just talk about a difference in potential energy. For electrochemical cells, we talk about a difference in voltage, all right? Just like we could assign, relative levels of potential energy to beakers filled with water, we can do the same thing for half cells like this. We can assign relative potential energies to half cells. And then once we do that, then we know, oh, okay, we connect this half cell to that half cell, water's going to flow this way, right? But as you know, the first thing we got to do is assign a zero. What is zero? Well, we just take a random electrode that we just decide to call zero, right? And it can be anything, but this is what some electrochemists decided many, many years ago is what we would call zero, right? It's called the standard hydrogen electrode, all right? And it has hydrogen gas and H plus at 1 molar, and the half reaction is 2H plus 2 electrons goes to H2, right? That's the reduction, and we're going to say that this particular electrode has a 0 voltage. Then we measure everything relative to that. Oh, why platinum? Good question. Notice that in many cases, the electrode, like in this case, zinc, participates in the reaction, okay? But when you have redox reactions that don't have any metal associated with them, you need some metal surface for the reaction to occur and for the electrons to travel through, right? And to get into the wire. So that's why you use something like platinum. It's very, very inert, and it acts as an inert metal surface for the electrons to gather and then go through the wire. Okay, so we call that 0, and then we measure all other electrode potentials relative to that. So how do we do that? We just make the standard hydrogen electrode and we hook up the electrode that we're trying to measure to that standard hydrogen electrode, and then we measure the voltage, right? If we hooked up zinc, we already know that zinc, yeah, that's why platinum doesn't corrode, correct. If we hooked up zinc, we know that the electrons there have very high potential energy, so they would go and travel in this direction, right? And we'd measure a voltage, and we'd say, aha, this half potential, this half reaction, or this electrode has a voltage of negative 0.76 volts. It's negative because of the electrons having higher potential energy at a negative sign rather than a positive sign. So the negative charge of electrons kind of complicates this a little bit. All right, if you do this with a lot of metals, you basically get this table, okay? And this is what I want to focus on, is this table, because this is all you really have to understand. Right here in the middle of this table is the standard hydrogen electrode. It has a voltage of 0, okay? Like we said. Anything below this table has a negative voltage. All right, and now here's one thing you have to remember. Do electrons go away from negative charge or towards negative charge?
Away.
Away, okay? So the lower you go on this table, the more negative the voltage, and therefore the higher the potential energy of the electron at that electrode. That's it's a little bit confusing, but if you think about electrons being repulsed by negative charge, right? Then you can say, oh, okay, down here, this has a -3 volts. That means that, aha, a lithium electrode is really going to repel electrons. Now, notice how this makes beautiful sense with other things you've already learned, right? You already know that lithium, right, is a particular kind of metal. Let me just pull up a periodic table here for you really quick. Right? Remember these group 1 metals, what do you know about them? What do you know about metals in this group? They're the
Plus
most
one charge?
active
+1 charge.
most active metals, right?
Oh.
They have a strong tendency to do what? What do metals do?
React.
Electrons.
Lose electrons, right? Lose electrons. So in other words, what we're seeing on this table makes perfect sense with what we already know about the elements, right? These lithium has a very high tendency. So if I put lithium with lithium plus, right? I'm saying that this reaction has a strong tendency to go towards the left, right? Not towards the right. Has a negative, very high negative potential. That means it has a very high tendency to lose electrons, okay? So think about it this way. Negative potential. That means high, oops, sorry, I'm covering this up. That means high potential energy for electrons, right? And that in turn means tendency to undergo oxidation, right? So things down here have a very high tendency to go in the reverse direction. These reactions are written as reductions, but that doesn't matter. You just have to write them somehow. But really, you just want to think about this as lithium, lithium plus, right? A balance between those two. Which direction are things going to go? It's going to tend to go towards the left, towards oxidation, okay? Positive potential, on the other hand, positive potential means low potential energy for electrons. And so that's going to have a tendency to undergo what?
Reduction.
Reduction. And let's look and see if this makes sense with what we already know. What do we see at the very top of this list?
F2 gas. Wait.
Fluorine, yeah, fluorine. And what do we know about fluorine?
Not very reactive.
Oh, it's super reactive, but it's the
One
miracle.
minus.
Most electronegative.
Very, very electronegative, right? Remember our metals and non-metals, right? Metals tend to lose electrons. These are the most active metals, the highest tendency to lose electrons. These are the most active non-metals, have a high tendency to gain electrons, right? So it makes perfect sense that fluorine is up here on the top of the list, right? High tendency to gain electrons, very positive electrode potential. Electrons have low potential energy at a fluorine electrode. Are you with me? Taylor, did you have a question?
Yeah. So is this why we make batteries out of lithium and like they're much higher than
Yeah.
batteries?
Yeah, exactly
And
right.
when you puncture them, they burst into flames.
Yep, that's exactly right. You're exactly right.
Okay.
Yeah, yeah,
Okay.
good. You know, I mean, I know sometimes I love it when you guys make these kinds of connections. Like, wait, is this what's happening in our brain cells? And is this what happens in lithium batteries? Because what we're learning here are the fundamental things that apply to everything that happens all around us all the time, right? And so these aren't just abstract concepts. These are actually very, very relevant and form the foundation for so many things, including nerve signals in our brains and lithium batteries and you know, Teslas and all the rest of it. Okay. So here's a quick summary, and then I'll show you how to apply this to calculate cell potentials, okay? The electrode potential of the standard hydrogen electrode is exactly 0, right? That's just assigning C level, all right? The electrode in any half cell with a greater tendency to undergo reduction is positive, right? Those are things at the top of the list, right? The electrode in any half cell with a lesser tendency to undergo reduction is negatively charged and therefore has a negative E0, right? These things tend to undergo oxidation. The cell potential of an electrochemical cell, okay, and this is E cell, is just always going to be equal to E cathode minus E anode. And we'll do an example of how to calculate that in just one moment, okay? E cell is positive for spontaneous reactions and negative for non-spontaneous reactions, all right? So a positive E cell tells you that that particular electrochemical cell is positive because that particular redox reaction is spontaneous. So remember, we said that a negative delta G corresponds to a spontaneous reaction. With voltage, it's exactly the opposite. A positive E cell corresponds to a spontaneous reaction, okay? A positive voltage means spontaneous, negative voltage means non-spontaneous. Okay, let's do an example. So we want to calculate the standard cell potential, E0 cell, for this reaction. All right, so what we have to do is we have to figure out, okay, what's the oxidation and what's the reduction? Now, one way to do that is to just assign oxidation states, right? But look, you can probably do this even more quickly now because you're starting to get a hang of this. What's being oxidized here? Can you look real quickly and tell me what's being oxidized in this reaction? This is a balanced oxidation reduction
Is it
reaction.
copper?
No.
Copper, right? Look, right away. Copper is being oxidized to copper 2+. So the oxidation here is copper going to copper 2+, okay? And there's 3s here in front of it. That doesn't really, well, we'll keep that there for a minute and I'll explain that. And then, of course, if we just did the half reaction, what would we need on this side? We need 6 electrons, right? Because 3 times copper 2+, the charge here is 0. So to balance that half charge, we need 6 over there, okay? And then everything else is the reduction half reaction. So the reduction half reaction is 2NO3 minus plus AH plus goes to 2NO plus 4H2O. That's the reduction, okay? So that's the reaction that's happening in the electrochemical cell. And our task is to find the standard cell potential, find E0. Find E0 cell. Now, E0 cell, we said, is E cathode, right? Minus E anode. All right? Which of these two reactions, these two half reactions, represent the reaction that's happening at the anode?
The reduction, I think.
Oxidation, right?
Remember we defined this. How do you remember which kind of reaction occurs at each electrode?
Anode oxidation.
Oxidation.
Anode oxidation, cathode reduction, right? So which reaction is happening at the anode?
The oxidation reaction.
This
So-
one. So this is
that's
anode, right? And which one's happening at the cathode?
That one there.
The
Yeah.
reduction.
Okay, so then all we do is we say, oh, okay, let's just look up these half reactions on the table. Okay, here's our table. I don't know, can you guys see this table? It's probably going to be pretty small. But let's see, do I have another? Oh, I have a little zoomed in version. Okay, does that look better? So we're going to go hunt for these two reactions, right? And so we start here at the top with F2, we come down. There is one of my two reactions right here. That's my, which one, cathode or anode?
Cathode.
Cathode, right? So my cathode half reaction says it has a voltage of 0.96. So I'm going to plug that in there, right? And then I'm going to keep going down and look for the other half reaction. And there it is. And that says, so I'm put minus because it's minus E anode. That's my anode reaction, right? See that? Now notice that this reaction is going from copper to copper 2 plus. Here it's going from copper 2 plus to copper. That doesn't matter. Remember, the way that this is written doesn't matter, okay? These can go right or left. It doesn't really matter. We had to write them one way, so we wrote them all as reductions, okay? But we could have easily have written them all as oxidations. It makes no difference, okay? This means that if when you have a copper 2 plus solution, this is the potential energy of the electron at that electrode, okay? So that's E cathode minus E anode, which is minus 0.34 volts, right? So that's equal to 0.62 volts. All right. So that means that a electrochemical cell made from these two half reactions would produce a voltage of 0.62 volts. Since this is positive, that particular electrochemical cell would be spontaneous in this direction. Okay. All right. Are you ready to try one of these? Let's have you try one. Calculate the cell potential for this reaction. And if you were to look up the half reactions at the table, this is what you'd find. Okay, let's do a poll. Alex, did you have a question?
Yeah, for the last one, you not have to multiply like the 0.96 by the stoichiometric coefficient.
Great question. Yes, and I meant to address that, so thanks for bringing it up. Since this is 3 and 3, right? But here it's just 1 and 1. Shouldn't I have to multiply this number by 3? The answer is no. Okay, unlike delta G's and delta H's where we had to multiply by the stoichiometric coefficients, okay, here we don't. Now, why is that? That's because the units of potential, the units of voltage are joules per coulomb, not just joules. So it's joules per unit charge. And that unit is more like a density, right? In other words, do you multiply the density of water by 2 if you have twice as much water?
No.
No. The density of water is the same whether I have a little bit of water or a lot of water, right? The density is the same. Similarly, the potential is the same if I have 1 mole of copper going to 1 mole of copper here, or if I have 100 moles of copper going to 100 moles of copper, right? It doesn't change. Yes, exactly right, Sophia. Extensive. This is independent of mass, so it's intensive. Okay, it's like density. All right. So you don't multiply by the stoichiometric coefficients when you're doing these calculations. Okay, go ahead and continue. Try to answer this question that this one. Yeah. Okay, try to answer in the next few seconds. Okay, very good. Most of you got that. The right answer was A. Okay. And so how do we get that? So we take the equation, overall equation here, we got to figure out what's oxidized and what's reduced. Right? So notice magnesium is oxidized. It's a pretty simple one, you can tell, because it's going from magnesium solid to magnesium 2+. Copper is being reduced, right? So there's your oxidation. Magnesium is being oxidized, copper is being reduced. Oxidation occurs at the anode. Reduction occurs at the cathode. E cell is E cathode minus E anode. So you look up, okay, the cathode is the copper. So that's 0.34 volts minus E anode. Anode is the magnesium minus 2.37 volts, right? And so when you add that together, you get plus 2.71 volts. Does that make sense? Question. Oh shoot, who was that? Oh, was that you, Taylor? Did you have a question?
Yeah, I think it was me. I don't know. Was there anyone else?
No, I think it was you.
Okay. So since we know the voltage and if I don't know if yeah, we know how many electrons are going through, can we figure out like the amps per mole? Like, because we know
Yes.
ampage.
Yes, that's the basically you can figure out the stoichiometry of the reaction tells you something about the current. So we'll get to that.
Okay.
A little bit later in this chapter next week, okay? We'll get to that very, very issue. Because that's a way to measure how much of the reaction will occur. In fact, you can control, let me explain it when we have more time next week.
Okay, no problem. Thank you.
Why do we add 2 electrons to each side? Because remember, each half reaction has to be balanced, right? So if you have Mg and Mg2+, right, we need 2 electrons to balance out the 2+ over here. Copper, 2+, copper, we need 2 electrons to balance out the copper, right? And we know that redox reactions involve electrons, right? So this is what's happening. The magnesium is losing electrons and the copper is gaining those electrons. Okay, we're almost out of time. Are there any more questions? Okay, great work today, you guys. Thank you for staying with me. I really appreciate it. Today's Wednesday. You have a problem set due Friday night, so make sure you get that done. You have, of course, a post-lecture due tonight. And we're well on our way. So thank you very much. I'm going to stop the class now, officially end it. If you have any further questions, I'll stick around afterwards and answer those, okay? Thank you, everyone. Have a great afternoon.